In this video, I'm going to talk about force and energy as it applies to simple harmonic motion. Please read the success criteria I plan to cover in this video. Let's take a look right here. I have a mass at the end of a spring, and if I either push it up or pull it down, it will undergo simple harmonic motion up and down. Now, you know that this spring can either be compressed, that's what happens when I lift it up, or it could be extended. And either way, it will apply a restoring force. A force, if I compress it by lifting up, it will try and push it down. If I pull it down past that equilibrium point, it's going to bring it back up. Now we know from Hooke's law, the force is going to be proportional to the displacement from the equilibrium, and K will be the spring constant. We also know that force equals mass times acceleration. Now if we put them together, we realize that the force is going to be directly proportional to the acceleration. F is proportional to x, it's also proportional to A. Now you might be saying, well, wait a second, what about the force due to gravity? Now realize if I didn't have this hanging, my spring here would not be stretched this much. The key to this is not the original length of the spring. We're actually putting the equilibrium line where it hangs naturally without it moving up and down. That means that the force due to gravity is not going to have a net effect, and we'll be able to have that simple harmonic motion. So let's think of what this looks like in terms of a graph. You can see I've got my sinusoidal shape here again. It is a periodic wave. We've got simple harmonic motion. And I've labeled up here A being a positive value and E being a negative value. If you think about it, right here, this must be C. Now, don't ask me why I have C being times 0, that it's moving. It could have been already moving and I've just said start now. Remember, if I move this mass up to A, my force would actually be pointing downwards because we have F equals negative kx. The force and the displacement are opposite directions. So if I'm going to have a positive force, that would have to be pushing upwards, and that would label this spot E. Back to C in the middle and A. If I want, I can put D's and B's in between these. C, E, and so forth. Now, let's change this up a little bit. Let's put that spring down here. And now my equilibrium line is going to be where my spring is at its natural length. It's neither compressed nor extended. I'm also going to say that this is frictionless, so I don't have to worry about the force of friction causing any issues. So if I compress the spring, I'm going to have to move it over here to A. And in that case, I would have a force pushing to the right because my spring is compressed. If I pulled it over here to E, then my force will be to the left because the spring is extended, and again I have this restoring force. I will have simple harmonic motion. But in this case, let's talk about energy. And in particular, for this simple harmonic motion, I have elastic potential energy stored in the spring, and I have kinetic energy. I've got here that I'm going to start at A. I'll compress my spring over here, and at this point, it's not moving. I'm just going to write here, V equals 0. So what does that tell me about my kinetic energy? Well, 1/2 mv squared. Kinetic energy must be 0. And my potential energy in the spring must be a max. Now if I let it go, it is going to cause my mass to speed up until we get to C. And at that point, it's going to be at its maximum velocity. It will then slow down as the spring is extended beyond its natural length. I'm going to write here then, V is going to be a maximum here. It's going to slow down and stop at E, so V will be 0. Correspondingly, my kinetic energy will be a max at C and 0 at E. If it's in the middle, it's its natural length. It's neither compressed nor extended, so there's no stored potential energy, and a maximum again at the end. And for B and D, I can put values in between the maximum and 0. So let's put this as a graph. I'm going to put energy on the Y. I'll put time here on the X. Now, I've labeled it here, start at A. So it's compressed. I'm going to have no kinetic energy. So let me do kinetic energy in this color first. Here's my legend. I'm going to have none here. I said I'd get a maximum at C. I don't know. Let's say right here is a maximum. I'm going to get to D and on to E, where it's going to go back to 0. Here's my maximum and back to 0. That's about as good as I'm going to get. Notice that I've only had one cycle here. I went from A to E and back again. Only one oscillation. But my energy here has gone through 2. So the frequency of the energy will be twice the frequency of the displacement. Let's do potential energy. At A, it would be its maximum. At C, it's 0. E, maximum. C, 0. Back to max. Again, in one cycle of my mass spring system, I actually have 2 complete cycles of my potential energy, so it has twice the frequency and half the period. Also note that energy is always positive. It didn't matter if I was at A or E. I still gave it a positive value here of energy. That's different than displacement, velocity, or acceleration. One last thing is if I did total energy. I'll do it in green. Now if this was frictionless, my energy does not dissipate, and actually it will be right here. If you think about it, this was a maximum and 0. So it's going to have to be here. Likewise here, maximum, 0. And in between this height and this height should be the same. This one's better drawn than this one. So let's do some examples. Example 1 says, I have a displacement time graph. And it wants to know where the maximum value of kinetic energy is. Now remember, for maximum kinetic energy, I need a maximum velocity. And where is that going to take place? At the equilibrium line. That's going to be x equals 0. The displacement equals 0. That means my answer is B. Okay, again, I've got my vertical spring this time. Just another example of simple harmonic motion. And we're looking for where the magnitude, so that's just the size, I don't care if it's positive or negative, at which point is the magnitude of the resultant force a minimum. And in this case, our minimum is actually going to be 0. If you recall, force is proportional to negative x if we have simple harmonic motion. So that means I'm going to have my force equal to 0 when x equals 0. And that's going to be at the center of the oscillation. My answer is A. Now this is a graph you might not have seen yet. I have kinetic energy versus displacement. And we know from our simple harmonic motion that when it's at A, it's at rest and it has no kinetic energy. And then it's going to speed up to a maximum at C and then slow down and stop at E. So this is actually going to be A, because my x is negative. This will be C, and this will be E. And what will happen after it gets to E? It's just going to go back. And kinetic energy will increase till C and back to A. So there is no second line for saying, am I going to the left or am I going to the right? It's all just this graph. So now we've done A. We've labeled the appropriate positions of A, C, and E. Now, draw a line of potential energy. Well, where did it get this kinetic energy from? Well, it must have been from the potential energy. I'm going to draw this in blue. Here it had no kinetic energy and just potential. And now all of that has turned into kinetic. So this must have been the original amount of potential energy it has. And if all of it's going to kinetic, then I have zero potential in the center. And then again, a maximum here. So let's try this. There we go. Label that P. It then also asks us to do total energy. And again, if this is a frictionless surface, then no energy will be dissipated, and my total energy will just be right along here. So that is everything. Please read the success criteria again, and hopefully you can say yes to all these pieces after watching the video.